remote lifestyle, well, I want a system that just always works. And especially when I'm on the road, I will typically reduce my working hours from about 10, 11 hours a day, 7 days a week. I will then work maybe 4 to 6 hours, 7 days a week. And especially when I have that
After testing the Gemma 4 model on my laptop and desktop, I decided to run a crazy experiment, to try launching Gemma 4 on my Raspberry Pi 5. Of course, I'm not talking about any large versions of this model, but rather attempting to run the smallest one, E2B. I'm not sure if this will work, since even the smallest model may still require significant resources, but it's worth trying. My Raspberry Pi 5 is on my home network, so I always access it via SSH. I don't even have a graphical interface installed on it, just Ubuntu server and a minimal set of software that I need. Hi, I'm Nick, and I've been developing software for over 20 years. On this channel, I share my experience, insights, and thoughts about IT. So I connect to my Raspberry Pi via SSH. I have the terminal multiplexer tmux running there. It's a very convenient and useful tool if you often work in the terminal. tmux allows you to keep sessions running even if you disconnect from another computer. Definitely give it a try if you're not familiar with it. Alright, first I launch htop so you can see the specs of my Raspberry Pi. Just to remind you, this is version 5. As you can see, it has 4 cores and 8 GB of RAM, most of which is currently free since I'm not running anything heavy at the moment. Okay, the first thing I need to do is install LM Studio. However, since I don't need the graphical interface, I'll install only the CLI version. You could call it a headless version of LM Studio. The developers provide a special script that handles everything for you. After installation, it suggests starting the daemon right away. Alright, let's do that. Now let's check what commands are available. I see a set of commands for managing models, some for managing the local server, and a few others that I don't need right now. In general, the commands are pretty straightforward, but before launching anything, I want to change where the downloaded models will be stored. The thing is, I have an SSD connected to my Raspberry Pi, so I want the models to be stored there instead of on the SD card. By the way, Raspberry Pi 5 introduced a simple way to connect SSDs and similar peripherals. I've been using such a drive for over a year now, and it's very convenient. Alright, the storage location is set. Now I'm downloading the smallest model from the Gemma 4 family. This model is called E2B, and it's about 4.5 GB in size. While it's downloading, let me briefly explain what it can do according to Google's announcement. First, the entire family of these models is designed with agent-based workflows in mind. They natively support function calling and can work with tools. Second, these models can handle images and video, and the smaller models, including the one I'm installing right now, also have native audio support. They can understand speech directly. And third, these models have a context window of 128,000 tokens and support almost all languages. By the way, Gemma 4 is released under the fully open and commercially permissive Apache 2.0 license. That means you can do almost anything you want with these models. Alright, the model has finished downloading. As you can see, it has around 4 billion parameters, which should be enough for simple and smaller tasks. I'm loading the model now. Okay, it loaded successfully and is ready to use. Now I'll launch htop again to see what changed after loading the model. Looks like the model has been loaded into RAM. Alright, the last step is to start the API server so I can interact with the running model. I'll use port 4000. Alright, the server is running, but just to be safe, I'll check if it's working properly. To do that, I'll send a simple HTTP request to get the list of available LLM models. In that list, I expect to see the Gemma 4 model I just downloaded. Nice. The API request was successful and I got the list of models, and I can see Gemma 4 in that list. Perfect, everything is working. However, right now LM Studio has started a local server that's only accessible on the Raspberry Pi itself. I want to use this model from my other computers over the local network, so I'll stop the server and restart it with an additional host parameter, setting it to 0.0.0.0, which should make it accessible on the local network. That didn't work. It looks like the host parameter isn't available, and I can only specify the port when starting the server. But that's not a problem. Since this is Linux, we have all its power and hundreds of utilities at our disposal. So there are plenty of ways to solve this. I'll go with the fastest and simplest solution, using the Sochat utility. It allows you to forward network streams within the system, which is exactly what I need. I'll forward the internal port 4000, where the LM Studio server is running, to an external interface on port 4001. This effectively creates a bridge between the internal and external ports. Now, any request coming to the Raspberry Pi on port 4001 will be redirected internally to LM Studio. Alright, now I'll disconnect from the SSH session on the Raspberry Pi, and so to speak, return to my MacBook. Now I'm in the regular macOS terminal. I'll try sending the same HTTP request as before to get the list of available model. But this time, not to localhost, but to my Raspberry Pi, which as a reminder is on the same local network as my laptop. Nice, it worked. As you can see, I received a response from the LM Studio server running on my Raspberry Pi. And in that response, I can see Gemma 4. Now everything is finally set up the way I wanted, and we can move on to the most interesting part. Actually testing Gemma 4 on the Raspberry Pi. Since the local server started by LM Studio fully mimics the OpenAI API, it means that any application where you can specify a custom OpenAI endpoint or base URL can work with your local model. This could be chat interfaces like Chatbox AI or OpenWeb UI, or your editors and IDEs. For example, VS Code Cursor or Z Editor. I'll be using the last one today. Alright, I open the settings in the Z editor and add a new entry in the LLM section for the Gemma 4 model running on my Raspberry Pi. Since I added a similar entry a couple of days ago for my desktop, I'll just copy it and update the server URL and the model name. By the way, I have a separate video about running and testing Gemma 4 on my MacBook and desktop. Now, if we go to the settings and open the LLM providers section, we should see an entry corresponding to a Raspberry Pi. And here it is. Okay, now in the chat at the bottom, I'll select the Gemma 4 model running on the Raspberry Pi so that it's used in this session. Let's send a simple prompt to check if everything is set up correctly and whether our local network setup works inside the editor. Alright, the model started thinking. That's a good sign, but just to be sure, let's wait for the response. Nice, the model replied. Let's take a look at the reasoning section. Looks pretty standard. The usual thinking process you'd expect from these models. So what do we have at this point? First, Gemma 4 is successfully running on the Raspberry Pi, even if it's the smallest version. Second, I'm able to interact with it from another computer over the local network. I think it's time to push this model to its limits. To do that, I'll connect to the Raspberry Pi via terminal and start monitoring system resources, so we can see how much load the response generates. Already, not only did the model write a sorting function, but it actually provided two different implementations and explained when to use each. Pretty impressive. However, the total time, including the reasoning phase, was about 6 minutes. I think this could be reduced a bit by disabling the reasoning mode, but overall you get the idea of the performance. Now for completeness, let's try a non-programming task. I'll ask the model to come up with 3 web app ideas. After a short thinking phase, which I've sped up, the model starts generating ideas. What you're seeing now is the real generation speed. From my perspective, it's about the same as in the previous task. I'd say this speed is right on the edge of what feels comfortable for a human to read in real time. But for non-interactive scenarios, it's acceptable. I'll speed up the rest again and check the total time. Alright, this time, Gemma took about 5 minutes to generate the full response, but it produced a lot of text and described each idea in detail. In my opinion, that's a very solid result for such a small model, especially running on a Raspberry Pi. So now you have the full picture of running Gemma 4 on a Raspberry Babe, are you
Thanks everyone for being here. Today I want to talk about what, but instead of that, let's address one normal situation. What happens on a day-to-day to everyone? Take this number, for example, totally made up. Lawyers happens, and this is a number that I just came up with. You have 30 microseconds to do a trade. Something comes in your pipeline. You have 2 micros to just decide what to do. You check your risk for 5 macros, and then sure, you want to hit it, so you have another 3 macros. You're hitting a market in Chicago, so approximately 6,000 kilometers, speed of light, 20 nanos. So that's your budget, 30. If you miss by 10 nanos, someone else gets the fill, you get zilch, and you start either losing money or not making money. And this is what happens daily, billions and billions of times. And it's not about your average speed, and no, this is the 99.9. This is like your worst thing. This is how you need to deal all the time, constantly. And there are very few languages that can give this to you. And one constant is that in those situations, the choice of computing language is not academic. It's not an experiment. It is practical, and it has to work all the time. And that is why most people go to C++. But with this thing, you know, there are a lot of things that we like about C++. We have, first of all, it's a language that gives you control and abstraction at the same time. And that is a great feature. And everybody has struggled with other languages that have garbage control and whatnot. And the worst thing that can happen is that at, 11, after some economic number release, you get a garbage collect of 5 milliseconds in the middle of the hot path, and you lose millions and millions of dollars. So having absolutely no garbage control, no garbage collection is great, but then you have memory layout, because one of the things that C++ gives you is full control over your cache lines, over NUMA cores, you name it, you have it all. So not only you have control over your execution path, you have full control and visibility of your data path. But then you want to talk to the kernel, but you don't want to ask permission to the OS. You're going to go directly to your network cards. You want to say, hey, I want to talk to my NIC directly. You can also do that. And there's no OS that you need to beg. Whatever you compile, whatever you get is what's going to run every single time. Predictable, 100% of the time. And these are all great features that we have had in C++ for many years. And we got complacent. We got complacent because we learned that with C++, it was more important to put the how than the what. We started handcrafting for loops and gotos in our code and loop unrollings and things that were really manual behavior, and you make it into a language feature. Take concepts, for example. We used to have all this obscure template machinery, all this. Then we had, in 2023, we started of data, like races under very bursty load when suddenly there's an increase in volume, cancels that were left behind hundreds of thousands of orders, or the typical machine bouncing a process at 3 in the morning, suddenly there's a deadlock and you get a call and you need to connect to the system and try to fix it manually, and you end up just nuking the process and starting a new one, which is terrible. And the worst thing is the overall, oh, I'm going to hope for the best. This is my strategy for like increasing like load. We no longer have that. Now we're going to start pipelining our processes, as you can see here, and start controlling where, how, why, and more importantly, what happens when we want to cancel or we want to stop. Everything is integrated. And fundamentally, this is part of the overall trajectory of C++ as a language. We started getting rid of the loop unrolling code, even though you can still do it if you want, because we realized that the compiler does it better for me. We stopped doing all these finite tricks that we used to like because we had nothing better. And we went to a place where concepts express clearly our requirements. With ranges, we stopped doing our for loops, and now we see that this is better. We have data transformation. It's clear. We just tell the system what we want to achieve, not how to do it. And all this ad hoc nonsense machinery for threading and pipelines and whatnot, that is gone with structured concurrency. So the language, if we need to put into 2 sentences what it does, it's telling us to stop coding the mechanics and start expressing intent. Because C++ is not just the best language for what we do today, it's the best language for the foreseeable future. I think that every single generation of the language, every single version gives us better tools and a better way to have more fun coding and less fun suffering. It's the nature of the beast. And this is my segue into passing the torch to Gasper, who's going to talk about execution. Because, again, that's the last frontier, at least for me.
I've worked as a quant in high frequency trading, $10 to $100 billion a day, just the strategies that I was responsible for. $10 billion a day is roughly the GDP of France. I was earning big fat paychecks as well, but I felt that I was wasting my life. High frequency trading is all about exploiting market inefficiencies. I saw how much money we were making due to simple structural design flaws in existing markets. People in trading just want to make money so they can earn big bonuses, right? I'm Anane, I'm founder and CEO of QFX. I used to work in the quant finance sector before I realized a lot of financial markets infrastructure is broken, and now we're building the next 24/7 global stock exchange, which is going to revolutionize trading. We had 2 major funds. One was General Catalyst, one was Nexus Venture Partners, round closed at 95 million valuation. We weren't making any revenues. We were pre-revenue, raised a 95 million valuation. The only point in raising venture money is if you can be massive, right? Like truly massive. Then a VC will find it very hard to say no. Towards the end of my time at Cambridge, we weren't very wealthy growing up, and job in quant trading by talking to people, you're just looking at data and you're trading from data. People ask me for like a real world analogy. I often say it's like running a car dealership. Somebody runs a car dealership, but I think there's a lot of cognitive dissonance amongst quant. And I think Tower has really, really high quality of talent. So a lot of my colleagues were International Maths Olympiad medal winners. There's this entrance exam in India for like the top technical universities called IIT. A lot of them were ranked in kind of the top 50 in India when they did this test. They're stuck in the same golden handcuffs. They're getting paid too much basically, and what are we doing in 5-7 years time? A very high valuation. I'm not going to defend SBF and say what he did a good thing or the end justifies the means. So that high frequency team pretty much. Josh worked at Citadel, but on the engineering side, he didn't know anything about the exchange side of things, right? He just called message some operator. He's like, oh, we got into everyone's result. Like somebody was plus $1 million, somebody was minus $1 million. You're like, oh man, we only gave them like $100 to play with. Like, how has this happened? So we had to basically spend all day reconstructing what had happened, figuring out how much money everyone owed and how much they didn't owe, reimbursing some people. That was the first time we took a loss as the company. We had to say, oh, we're sorry. It says that you're minus $100, but we don't think this is right. We'll just give you $100. Luckily, it was still small scale. It wasn't like a big loss for us. The issue was it really hit home how difficult it is to build a 24/7 perfect, fully available system that keeps track of. If you run something 24/7, like anything can go wrong anytime, right? Lightning bolt can happen, fire in the data center, whatever. We didn't sleep properly for days after that because we were like, we don't want this to happen in life, right? Because if we do, it's game over for us in exchange. I think the reason the partners made us do it is to basically make us grow up and realize the gravity of the situation we were in. That was a really tough time. Both the best days of our life and the worst days of our life, we were working all the time, like 100 hours a week, very focused, very frenetic. There's some misconceptions maybe about how fundraising happens in Silicon Valley. It's very quick. If the check size is less than 500K, typically it's a 30-minute meeting and you get the decision like on the call or just after. If it's kind of a bigger check, then we had a first meeting and a second meeting in person, which was both for 30 minutes, let's say roughly. And day one, we had a bunch of angels. We got some money. And then we stopped taking angel money. Yeah, then it was about the bigger funds. So we had 2 major funds. One was General Catalyst, one was Nexus Venture Partners, round closed at 95 million.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem flatten binary tree into a linked list. We are given the root of a binary tree and we want to flatten it so that it turns into a linked list, not necessarily a true linked list, because this data structure obviously is made up of tree nodes, binary tree nodes, where each node has 2 pointers, a left pointer and a right pointer, but they want us to condense it into a linked list where we're not really making use of the left pointer, right? For each left pointer of each node, it's just pointing at null. The right pointer is what we're actually going to be using, which is going to assemble all of these nodes into a linked list. So this isn't too difficult to do, but there is a catch. The ordering of the linked list should be the same as the pre-order traversal of the binary tree. Now, this isn't as bad as it sounds. This is actually going to make things really easy for us, and let me tell you why. We know that a binary tree like this one is, a recursive definition, right? A root node like this one could have children, and then its children are basically also trees themselves, right? This is a subtree, the left subtree, and this is the right subtree. When they say it needs to be the same as the pre-order traversal, the linked list needs to be the same as the pre-order traversal, what they mean is if we want to flatten this entire tree, the root node is going to go first, right? Because pre-order traversal processes the root node first. So good thing is we don't have to make any changes to the root node. Then what is going to come next in our linked list to the right, we want to do the pre-order traversal, right? So we want to process the entire left subtree, meaning we want to flatten the entire left subtree first, right? We want to flatten this entire right subtree and then stick it right in the middle over here, right? In between the root node and in between the right child. So once we flatten this thing, it's going to go in between. And then pre-order traversal then will process the entire right subtree. So then basically we want to flatten the entire right subtree. In this case, the entire right subtree is already flattened, right? It's made up of 2 nodes. And it's already flattened because there's no left child for any of the nodes here, so it's already flattened. So really, in this case, our job is to flatten the left subtree, stick it in here, and then we're done. But okay, how do we flatten the left subtree? It's a recursive definition, right? So we're going to apply the exact same recursive algorithm here as we would on the root node. So, okay, in order to flatten this tree, first we have to process the first node. Okay, it's a root node, so it's not going to change, right? Pre-order traversal. This node goes first. It's going to stay exactly where it is. Then we're going to flatten the left subtree. It's already flattened. It's just a single node, right? So this node is going to go, now that it's flattened, it's going to be stuck in between here. The 3 is going to go here. And then the right subtree here is also going to be flattened. It's already flattened, so no changes are going to be made here. So really, we're going to get rid of this node and instead have a 3 over here, right? So this is what the flattened is going to look like. Then once we're done with that, this is going to get stuck in between here, as you can see in the output. That's what happened. So all of that, hopefully that logic, that general recursive logic of this algorithm makes sense. It basically follows a pre-order traversal. Now, the only challenge that we're going to have is when we do flatten the left subtree right over here, you can see we flattened it, and then we stick it in here. How are we going to stick that flattened subtree or that linked list here? Well, of course, the root node, which over here you can see initially it's pointing, at its right child, but we want to disconnect that pointer. We want it not to point at its right child anymore. Instead, we want it to point to its left child over here, right? Because we want to stick this in between. So we're going to reassign the right pointer, to be, it's a little bit messy as I'm drawing it now, right? But cross this pointer out and then stick that right pointer to actually point here. And then we want to change the left pointer and have it actually point to null, right? Because the left pointer should always be null. So that's what we're going to do to the root node. And so the last thing we want to do is the end of the linked list, right? The end of the left subtree, it should be pointing at this node over here, right? It should be pointing at the right child of the root node. So the only thing we're gonna have to remember is to actually get, as we're doing this algorithm recursively, we're gonna make sure once we have flattened the entire left subtree, we have to return a pointer to the last node, or rather the tail of the linked list. If we have the tail of the linked list, then we can connect that pointer over to the right child of the root node, which is what we want to do, because in the output you can see, right, this this linked list, the left child linked list, has to be connected to this, which is the right child linked list, right? This is the right subtree, the right flattened linked list. So in order to do that, we have to make sure that we return the tail of the linked list so that we can actually connect these pointers. So that's the main idea of the algorithm. We are going to do it recursively because that's kind of the easiest way to logic through it, but you can do it iteratively as well using a stack to traverse the entire tree. But since we are traversing the entire tree, the overall time complexity is going to be big O of n, and where n is the number of nodes. The memory complexity, since we're doing it recursively, we're going to have a call stack for the memory. It's going to be, the memory is going to be a big O of h, where h is the height of the tree. Worst case, h ends up being n. But yeah, so that's the time complexity. Now we can get into the code. Okay, now let's get into the code. So they do say that this function actually doesn't need to return anything. All we need to do is actually just modify the tree and return the list tail, right? Because we do want it to return something. That's the main reason I'm defining another function rather than just using this root flatten function, because this function is not supposed to return anything. But here, and before we even finish the function, I always just write the recursive case and just assume that it's going to work. So when we run DFS, of course we want to run DFS, or rather our flatten algorithm, on the left subtree first, and then we want to run it on our right subtree. So assume that this DFS call is going to flatten the subtrees. What is it going to return? It's going to return the tail, right? So if we flatten the left subtree, then we're going to return the left tail. So let's assign that. And if we flatten the right subtree, we're going to return the right tail. Now, last thing we need to do is actually connect our our linked lists, right? So we're at a certain node, we're at the root node, right? We have a left linked list that's been flattened and a right linked list that's been flattened. And remember, we want to connect them. Now, only edge case you have to remember is, what if one of these lists is empty? What's going to happen if both of them is empty? Then we don't need to do anything, right? If the right list is empty, we still need to take the left list and then, move it over to the right side. If the left side is empty, but the right side is not empty, we have flattened the right side, but we don't have to do anything because it's already on the right side of the root, right? And the left is already null, so we don't have to do anything. So the only case where we are going to do a insert operation is if the left tail is non-null, right? That's the only case where we actually have to do the insert. Now, this pointer manipulation can get a little bit abstract, so feel free to draw out a picture if you want, but we're basically going to be following what I did in the drawing. So remember, we have a left tail, and we want the next pointer of that left tail to be assigned to the current right child of the root, right? So root dot right. So this is basically inserting, attaching the left linked list, attaching it to the right linked list. And we also have to make sure that the root is also attached to the left linked list. So we have to say root.left or root.right is going to be set to root.left, right? Because this is the tail of the linked list, right? But we want the root's right pointer to be at the beginning of the left linked list. And what's going to be the beginning of the left linked list? It's just going to be the left child itself. Feel free to refer back to the drawing or draw it out yourself if you need to for this. And remember, the last thing we need to do is the root we want to make sure that its left pointer is set to null, right? So we're going to do that last, obviously. We're going to say root.left is equal to null because, we have to do it last because we are using the root.left's original value in this statement up above, right? And the reason why this line goes second is because we're reassigning root.right and we are actually using root.right in the line up above. So this order that I wrote these 3 lines of code is not random. We had to do it this way because we had to use the original values of the pointers before we ended up changing them. But this is basically it. This is the entire insert operation. And then setting the left to null, and we're only going to be doing that if the left tree is non-null, right? And instead of even using left.tail, we could even just say root.left is non-empty, if this makes more sense. Either one is fine, I believe. Okay, and remember the last thing. Remember, this DFS is supposed to flatten, and it's supposed to return the list of the tail, or the tail of the list. So what is that going to be? Isn't it true that the right tail, the right subtree's tail is going to be the tail of the entire linked list or the entire tree? Like, isn't that true? That makes sense, right? The right tree's tail is going to be the entire tail. But what if the right tail is null? What if the right subtree was empty? Then what's the tail going to be? Okay, in that case, the tail is going to be the left tail, right? But what if the right subtree and the left subtree were empty? So, these tails happen to be null. In that case, the tail is going to end up being whatever the root is, right? Because the root is the only node. It doesn't have any left or right subtrees. So this is the order. If this is null, then we return this. If this is null, then we return this. You could write some if statements depending on what language you're using, but at least in Python, a little easy and neat way to write this code out is to do with Boolean. So, just put an or in between each of these. And the reason this works is because the way Python evaluates it is if this ends up being non-null, then last will be assigned to the right tail. If it is null, then it'll look at the next value and say, okay, is this null? If it's non-null, then this is what's going to be assigned to last. If both of these are null, then this one will definitely be non-null. And this one will be assigned to last. So, and then we can just return last. So it's, kind of an intuitive way for me, at least, and a concise way to write this out. So that's how I'm going to do it. You could do it with conditionals if you want. And then all we really need to do is call the flatten function, the DFS function, passing in the root node. We don't have to return anything because remember our root function, flatten, doesn't require us to return anything. So just calling this function is good enough. Okay, and actually just caught a quick typo. So in this line, for some reason, I wrote left tail.next when we actually want the right pointer of left tail, right? Because we're actually using the right pointers. So sorry about that. I hope that you caught it and it wasn't too confusing, but otherwise let's run the code and it does work. As you can see on the left side, it is a linear time algorithm. It looks like the time complexity isn't super efficient for whatever reason, but I don't pay too much attention to that. So I hope that this was helpful. If it was, left's original